we should get started. I'm terribly short of which I do. Okay, so welcome to the seminar. The speaker is Krishna Murthy. Just that's okay. Yeah. So very pleased to have him here. He's a postdoc from MIT, where he's been working with Antonio Diablo and Josh Turnenbaum. Did his original degree in University of Montreal, and has a history of doing very interesting work on vision for robotics or robotics vision, whichever way I put it for. And the work here has been about structured world models for robots, which I think ties in very well with a lot of the themes of the work at Hopkins, embodied AI type ideas, bringing together language, vision, and robotics. So, thanks. Okay.
Right. Yeah, it's good to be here. Thanks for taking the time. And today I'm going to be talking about structured world models for robots. And what I'm basically interested in is, I'm interested in teaching robots how they can understand the world around them. So for me, like robotics is a very good excuse to be working on general purpose AI systems, because robotics has a lot of unique challenges that just don't exist in the other domains. So imagine you have a robot in an environment like this, and you give it general purpose tasks like find your key, or maybe find shoes that match an outfit. And these tasks may seem very simple, like on the outset, but these are extremely challenging even for the best AI systems we have today. So let's try and think about what solving these tasks entail. So to make meaningful progress towards these tasks, robots must know what is where in the world. So have some representation of the world, knowing what exists and where everything is. And then in addition to this, you need to interpret the values in which these tasks have been provided. So interpret the context. So what outfit is in question for which you need to find the shoes. And then once you have the context and the representation of the world, you can then go about planning actions to achieve these goals. And today I'll try to outline like how much progress we made so far in getting to some of these goals, and actually see tasks very similar to the ones I showed here being deployed out in the real world robots. And I'll also outline like how much progress is still remaining to be made and how we might get there. So if we look at how we as humans go about solving tasks like these, there's many cognitive theories that support the idea that humans have these mental world models. These are basically internal mental representations that we build to simulate and reason about the external world. And these are ultimately just based on our prior beliefs, and these can be updated as you get new evidence, and these drive rational predictions and goal-directed decision making. So consider the amount of information you are able to recover from this video sequence. So just by looking at this video sequence captured by a camera moving around the room, you are able to infer that the world, you are able to infer the 3D structure of the world, and also the fact that the world is made up of these constituent, meaningful sets of objects. And not just this, you can also impute, so you can fundamentally impute all of these missing sense data. Even though you're looking at a 2D projection of the world, you infer 3D structures and objectness. And you can also perform you can use these models to predict what might happen. So if I were to turn a little to my right, what would I expect to see? And then you can use these predictive capabilities to plan actions for specific outcomes. So how do I get from here to the door? What kind of skill applications enables these kinds of behaviors? And you can also update the more important and interesting thing that I'll return to the second half of my talk is you can query these models for a variety of tasks. You can ask, why did this particular thing happen, and how can I make something else happen? And then we can also update as new evidence is obtained. So in a lot of my work, I try to take inspiration from what world models do to natural intelligence and try to take some of these aspects into artificial systems. If you think about the kind of AI systems we have today, and there's like a set pattern here where have a lot of these incredible demonstrations and progress across all of these domains. And the unifying factor across all of these, like if you were to take a state-of-the-art architecture or model for any of these domains, you'll start seeing a common pattern. Like all of these domains, progress is driven by these large transformer architectures, trained on very large data sets on large amounts of compute. So clearly scaling, and there's lots of studies to show that scaling is really important. There's lots of capabilities that emerge at larger scales of data, one sizes of compute that simply don't exist at smaller scales. But is it, it may not be sufficient. So to see why that may be the case, we start looking at the domains where scaling has been successful so far. So you can look at all of these domains where you have billions, trillions of data points on the internet to train your models. But now let's start moving towards the real world. And one intermediate step to think about is, what about 3D perception? And there's a lot of 3D content on the internet, maybe like 10 million data points, whatever these units may be. There's like millions of objects, mesh models of objects, and there's tens of thousands of 3D scenes, but all of them static scenes. So how do you, there's already like a big 4 or 5 orders of magnitude jump in terms of data we don't have. But then we're also just talking about static scenes. What about like dynamics and capturing all the rich variations of the web? And as you keep moving closer and closer, so for example, there's this open cross embodiment data set, which has 1 million data points with robot actions. So you run into this issue of you're getting closer and closer to the real world, but the amount of data you have so it decreases while the complexity of the domain increases, and it's certainly more evident in robotics. So how do we reconcile this trade-off and design the next generation of robot learning algorithms? And the one solution pattern I've used in most of my research and will continue to is notion of structure. Like there's lots of structures in the real world, lots of phenomena we know about, which can make learning faster and from less data, and you can also be more robust while not being needed complex. So my overall research vision is to build structured world models for robot learning. And there's many ways in which people can define world models. And here is my definition to set context for the rest of the talk. And by a world model, I mean any computational model can be fully learned, fully handcrafted anywhere in and that incorporates all of your prior knowledge and is able to perform predictions about both structural and dynamics aspects of the world. So it's not just dynamics model, you can also use predict structure, semantics. But the most important aspects of them is that they're variable. So you have a model that we can introspect or intervene on and ask various questions like, where is this particular thing? And how might something happen? How can I make something happen within this model? Or how can I use this model inside of planning? And by structure, I've leveraged lots of different kinds of structure, like 3D projective geometry, physics, computer graphics, priors we have from all of these areas to build structured models that can be used for robot perception and learning. And just as a very quick overview, my research has, I can classify my research into 3 broad areas. So there's spatial understanding, which corresponds to the mode of understanding what is where. And there's physical understanding, which is which just tells us what could happen in future. And there's multimodal understanding, which gives us a sense of how we might integrate sense data from various modalities to form a richer understanding of the big world. And in today's talk, I will only focus on these 2 aspects, the spatial and multimodal understanding aspects. I will return to physical understanding a little bit after I know about my teaching work, but I'm also more happy to chat about this one-on-ones. So let's start with spatial understanding, and let's think about what kind of world models can be built for robots to effectively understand the space environment. And in the robotics community, and a very close parallel can also be made of the computer vision community. Building models of 3D spaces has typically been dealt with through a lens of SLAM, or simultaneous local mapping, and robotic community, or structural motion, computer vision community. And the idea here is that there's two key problems. Like, imagine you have a robot that's dropped into an environment that is never seen before. So there's two key problems that robot needs to solve before it can start making sense of the environment. And the two problems are, these are intertwined problems. The localization problem, understanding where the robot is with respect to the environment, and the mapping problem, which corresponds to understanding what is around the robot, given where it is. And this has occupied a lot of literature in the robotics community, especially in perception state estimation, for like 3 or 4 decades now. And at this point, we're just starting to see mature SLAM solutions that can understand space around them, but still limited in many ways. And that's what my second half talk will revolve about. But so most robotics literature that revolves around building spatial models tackles this problem called SLAM. And SLAM amounts to solving simultaneously the localization, or the where am I, and the mapping, or what's around me. And this is sort of chicken and egg problem. Like, you need localization, you need to know where you are to know what's around you. You need to know what's around you to be able to pinpoint where you are with respect to that map. So this is, in many cases, like it's this intertwined chicken and egg problem. And the key idea or insight in the community has been, like, we want to build a consistent, so the model of the world we see is one that best explains all of our observations. So the goal is collect a bunch of observations, which could be images or depths or LiDAR or radar percepts, and then build like a consistent model that can explain as many of these observations as possible. And a lot of SLAM solutions fit like structured 3D models to sense data. And there's a lot of leeway in how you define these structured 3D models. And that's exemplified by some of the examples you have here. Like, there's 3D models which assume the structure is the world is a set of 3D points, and you are tracking all of these points over time, and you're adding new points as they arrive. And then the other end of the spectrum is dense SLAM, where you don't make any distinction. Every single point that you see in every single image must exist in your 3D. And there's all sorts of intermediate representations between polygons, lines, objects, and then there's also more recently implicit neural representations where a tiny neural net becomes your model, and you're updating the parameters of the weights of the neural network. And that becomes the structured 3D model that this eventual output SLAM system. And the second question has always been, and it's been for like last 30 years, it might well continue to be for the next 30 years, because it's such an open-ended problem, is what should the map representation be? So part of the reason a lot of these representations exist is because people haven't yet figured out what the ideal representation is. And so this is a very quick thought experiment to start thinking about what representations, like what are the desirable properties of some of these representations. So think about this task of chopping a bunch of vegetables. What is the ideal map representation here? Like, is it at a pixel level? Each single pixel deserves its own like location in a 3D map? Or do you group it by vegetable, or do you just group it by each chunk of vegetable? And this, if you move to a very different context, like books and library, is it like each book single representation, or is the atomic entity like a rack or a shelf, or neither? And it becomes more complex as you start going out to other kinds of environments. And you can see that if this is the scale at which you choose to represent the world, it clearly won't work in a scene like the one shown right. So again, the story here is that there's no single representation that works across stuff. And maybe the ideal solution is you want to have all of these representations, and then you want to pick what works for a single task. But with SLAM, it's always been, so in the previous slide, the way I show all of these various design choices is that SLAM people have typically worked slightly independently from the people actually doing control or consumers in the SLAM system. So I would build a SLAM system and then give it to a practitioner, and the practitioners would use it. They'll come back to me saying, well, your SLAM does not work. So there's lots of disconnects between the perception engine, like the SLAM engine itself, and the downstream task it's being used on. So these are just to very quickly provide like the issue is like these are map centric. So they just care about what the map is like, and they don't really read into or care about the task at hand. Depending on the task, your map take a very different form. So one of the ideas that came up early on in my PhD was, what if SLAM weren't viewed as a system building problem in isolation? Like how do we connect a SLAM problem to a downstream task problem? So can we optimize representations for SLAM based on a downstream task? And again, the goal here is let the system choose the best representation for the task. And we do so by leveraging task laws or like task performance gradients with respect to the task performance. And the way we do this is by taking a SLAM system and realizing that SLAM system as a differentiable program so that it plays well with all the neural network machinery you have so far. We have like very sophisticated differentiable programming frameworks. So can we express SLAM as a differentiable program and then leverage task gradients to backprop and figure out what the ideal representation is? And this leads to first work I discussed today. This was back in 2020, so the actual work was done in 2019. But just to give you an overall idea, for here, I'll be talking about dense SLAM systems for a while now, which means you have RGB plus depth images, and then you want to build a dense 3D map. Like you want to map every single point in every single image in 3D. And the choice of representation here is what I showed at the start of the point cloud, but we have a lot of other alternatives that our system supports. But this is just an oversimplification for illustration sake. So the idea is SLAM is a mapping from a state sense data to a state estimate. And the state estimate is a map of the environment and trajectory of the camera. Now, if you start thinking about this as a differentiable program, a gradient through this SLAM system basically expresses how your output changes as a function of your input. So if I were to cause small perturbations to my input, so if my input images and depths were to change a little, how would the outputs change? And I can use this to solve an inverse problem where I have, let's say, a desired output. What kind of inputs do I need to affect that output? And I'll make this more concrete in one slide, for example. And to set context, if you take away all of the details, like all of the actual implementation details away from SLAM, it is an optimization problem. It's a problem of you have a model specification, and in a lot of SLAM or structured motion algorithms, you have locally linear models with additive Gaussian noise, which tends to work very well, and which is in fact the most sophisticated systems we have out there today deployed in VR headsets and on your phones. And you take sensor observations and you optimize your model so that it explains all of these observations or as many of these observations as possible. And this is cast into a nonlinear least square style optimization framework where, and I'm just illustrating like a 1D slice or loss function. These are obviously like hundreds of thousands of variables if you talk about like a large scene. But you start with an initial guess on slot landscape, and gradient descent could seem like a simple strategy which tries to find a local minima for this loss function. So essentially, the workhorse of SLAM, motion, in this case, like bundle adjustment, is some kind of a nonlinear least squares solver. In this case, gradient descent. But you can do something smarter, like if you want to actually leverage the curvature information and descend much quicker, especially in real-time systems, this is an important concern. So you can do something like Gauss-Newton, where you start out with an initial guess, and you take a step and project it onto this function, and you are leveraging like curvature information, you're taking like a local linear approximation and performing a Newton step for that linear approximation. But then this also has issues when functions are ill-behaved. So in this case, where the function is near singular, where your initial guess is not a good starting point, or you have lots of motion blur, so the loss landscape isn't too great. And this will happen far more often. You will diverge. So then there's this algorithm which is fast but has no guarantees for divergence. And most solvers of that exist and are mature use this technique known as Levenberg or LM, which is a compromise between the two. So LM basically will take a step, but instead of committing to that step, it'll do a look ahead operation to see if the step actually makes sense. And in this case, the step increases the loss, so it doesn't make sense. So what it does is damp. So it makes you take a smaller step, scale back, and try half the step size. So now when you take a smaller step, that succeeds. And if that doesn't succeed, you just keep scaling back and back until your outer steps or until you find some step that's valid. So this is the kind of solver that's mature out there and it's used very widely. But the problem is that this is not differentiable because you're just essentially oscillating between, well, I'll damn and maybe do 10 steps of look ahead and then pick the next solution. So there's not a computation you can very easily express as a differentiable alternative and get gradients through it. So one of the things we did was to reparameterize this Levenberg one-point update rule as a logistic function. So if you think about classification problems in machine learning, you need to make like a true versus false in case of binary classification problem prediction. And the way you do that is by relaxing it into a smooth logistic, a continuous logistic function, which has like a steep transition. So in this case, we have a mapping, an interesting mapping between how LM iterates between gradient descent versus Gaussian style behaviors. Like, do you pick the gradient descent update versus Gaussian update? You can think of like this damping and undamping phase as two different endpoints of this function. It's just that they're not from 0 to 1 any longer. It's a generalized version of this function that goes from a minimum damp factor to a maximum damp factor. So you can reparameterize this into, I'll skip some of the details here, but the idea is you can reparameterize these step function changes into a much smoother logistic function. But you get a much smoother reparameterization. And then these gradients, so now that you can differentiate through the system, you get interesting capabilities because of these gradients. So you have an image here, and this is a bunch of RGB images. I'm just showing the first image for simplicity. You run this through SLAM, and you get noisy reconstruction because there's often that noise. And if you compare this with true reconstruction, in this case, a reconstruction obtained from clean text images, and you backdrop, you get gradient magnitudes for every single image pixel. And for a moment, let's consider an alternative case where you have the same set of images, but then you crop out, like you just zero out a bunch of RGB depth pixels in the middle. So when you reconstruct this, you get a hole through the reconstruction because there's no data there, depths are 0, which are just then removed during post-processing. And you then compare it and get gradient magnitudes of each pixel. Now, if you start comparing the difference between these two maps, you'll see that the difference in gradient maps is almost entirely due to these pixels containing included, basically meaning that you are able to track changes in the output of the SLAM system to the individual pixels in the RGB and depth space that caused these changes. So the differentiable computation graph is working as expected. So this is another example where we spawn like an occluder here squared between the scene and the camera, and we move that around, and in each case, you are able to track all the changes back to the original pixels that caused the change. So now you have this mapping between something you can define on the output of the SLAM system to the inputs, the input RGB and depth data. So one of the things we did was, what if we corrupt some of the images? Can we like impute these missing observations? So here we corrupt the RGB and depth channels, And after about 400 iterations of intent, we are able to recover like the RGB and depth images by pulling in information from the neighborhood views and by leveraging tree consistency. And you can see that even though the original depth data has like missing ground truth depth data has like missing objects, we can get soft interpolation guesses for what might have been there. And we also extended this in an application where we wanted to pick good features to track for ego motion estimation. So ego motion estimation is a very fundamental problem where you have these sequences of images and you want to estimate how much the camera is moved between these two images. And whenever there's like moving objects, they tend to corrupt the ego motion estimation a lot because the estimate computed by the static points is not the same as the one you get from the moving points. So what you see here is we train a model over a small data set as to predict confidence scores for how much each pixel should contribute to an ego motion estimation loop. And this entire thing can be made differentiable because we formulated this differentiable nonlinear least squares optimization. And after training, this is evaluation in a held out test set. And you can see that so black and gray mean lower confidences, the values close to 0, and green means higher confidence. And you see that shadows on the road and moving vehicles, they tend to get downweight. And the model learns to impose higher weights to static constants. And if you roll this forward, you see that using these confidences, you can get the curve in orange, which is much closer to the output, it does not drift. So the curve in blue here, which uses which assigns the uniform weight each pixel units. And one other thing is, so far the supervision signal we needed was to be definably output of the SLAM system, which is a 3D mount. And that necessitated supervision in 3D. And using modern neural rendering techniques, we could close that loop by running a differentiable SLAM pipeline and then rendering them out, rendering the representation to get 2D images back and comparing those images to close the loop. And the rendered images and recent sized images must match the original images that we started out with if everything went well. And this is a recent preprint, well, this is now at CVPR, where we use a more modern representation in form of Gaussian splat to optimize these scenes. So very quick takeaways for this segment of the talk. So incorporating algorithmic priors from structures you know from projective geometry, in this case SLAM or structural motion, and we do this via differentiable programming, where we implement SLAM as a differentiable program, and that allows us to include missing data, allows learning map representations like here with adaptation. So I will quickly switch here to talk about, well, we now have ways to construct 3D maps, and we have ways to.
Actually, there was a question there, please.
Yeah, there was a small question, sorry, before you transition. So earlier in your motivation, you mentioned that you wanted to learn SLAM in a way that is specific. But I'm not sure if you really connected your differentiable SLAM there to tasks yet, or maybe this is gonna be forthcoming.
Oh yeah, so this is where in the next section I will talk about tasks, and we'll connect to some of the tasks I showed earlier in my talk, like finding matching shoes and finding certain objects that are specified as a abstract. But yeah, so far we've just seen how we can design priors, like we can use priors from SLAM systems, like as opposed to treating SLAM as something independent from the task, where SLAM systems designers don't talk to other consumers of that pipeline. We can bring both of them together by implementing a differentiable version of SLAM. But now we'll talk about how can we enhance, like you have 3D maps, but how do we enhance them with higher level semantic maps?
Yeah, so should we be thinking about this as just fitting into the framework of multitask representation learning? So just if all the tasks are differentiable, then you can just learn common representation.
Yeah, so ideally you want like a general purpose map that can cater to a very wide range of downstream tasks. And you also want the task, like the map representation to be optimizable with that broad suite of downstream tasks. But admittedly, like the example I showed above was catering to just one specific task. But now I'll show general purpose map representations that can cater to lots and lots of tasks. And there's work done to connect both of these paradigms, which I haven't done yet, but that's very ripe for exploration.
More question. So I missed some of the details in the first segment of your talk, but like just to verify my understanding of the high levels of what you're doing there. So the way you're thinking, SLAM is an optimization problem, and you're doing an optimization over an optimization.
Yeah, so in many senses, this is like an outer loop optimization or the inner loop optimization problem that is SLAM. And my approach was to make the inner loop differentiable so that you can use this inside of a gradient-based optimization loop. And there's ways to have that outer loop not be differentiable and still use it in like a black box optimization scheme. And we can chat more about this after, but yeah, happy to take that on. Okay, so for the rest of the talk, I'm going to be talking about, so there's lots of advances in vision and language processing that we all know about. How do we leverage all of these advances to build like next generation of mapping techniques that can help robots accomplish lots of tasks that are specified very abstractly and perhaps even ambiguously, but more naturally? So some of the examples of tasks you might wonder what to do are, so here is like a robot trying to find something to wear to a space-themed party, and then it comes up with this t-shirt that says NASA written on it. Or you might want a robot to pick up something ready to eat, and there's like a mango that it picks up and drops into the tub. Or you might also just like find things shut from ringing, but I'll skip to this other query where someone knocks at the door and you want to listen to this door knock audio and identify what objects in the scene could be producing this. And these are not just didactic examples, these are like actual demonstrations that we've been running on robots for the last year and a half. And I'll tell you a bit about how we do this. So in the context of SLAM, if you wanted to incorporate any sort of high level priors about what are objects or what segments, like what are semantics of a scene, the way to do that has been like to re-engineer like a SLAM system from the ground up and take existing like semantic segmentation or object detection networks and fuse all those predictions securely. And there's been lots of progress, like starting from SLAM++ back in 2013 to like 3D scene graph style implementations. These were back in 2022. And there are some things that some common patterns across all of these approaches. So the first assumption is that there's it's all a closed set or closed web. All of the categories that are interesting to you are known a priori at training time. So here, as you can see, there's like probably 14 different classes or like 30 different classes, and then there's everything else plugged into this unknown class that you don't care about. Or the other thing is they also tend to be unimodal. So to query these, you have to take like semantic vector of chair and then figure out which pixels have a higher prediction for chair compared to anything else. And these also tend to be sensor specific. But then if you look at what computer vision has been doing and language processing has been doing over the last couple of years, they moved away from training for specific tasks to training general purpose feature implementations. So for vision, you have general purpose features like Dino, which are trained over web scale data, and you can apply them to your task of interest by something as simple as linear probe tuning. Like you can add a linear model on top and you specialize it to your task. And another model that integrates multiple modalities. So in here, like the clip model that tries to reconcile vision and language modalities. And vision and language are not the only two modalities where clip has been applied. It's also been applied to other modalities, including audio and 3D. But a very quick, like a one slide idea of how it works is you take millions, hundreds of millions of image text pairs, and then you apply a text transformer on the text pairs, an image transformer on the image pairs, and then project that to latent space. And you pull representations of the same image together, same image text pair together, you push everything else apart. And you do this at scale, and lots of interesting behaviors emerge. And one of the interesting behaviors is you can now do zero-shot classification, where like your class or category of interest is just specified at inference time. So imagine you want a plane versus car goes down with a bird classifier. And all you do is you come up with a prompt that says a photo of a plane or a photo of a car, and encode these prompts using text encoder. And you take an image, you encode it via the image encoder, and you compare, you compare both these embeddings in terms of cosine similarity, and the highest similarity class is picked. So you can create classifiers for new tasks online from like a web scale retraining implementation. So this was very influential in computer vision, particularly 2D computer vision. And our idea was, can we extend this to the 3D domain? Can we build 3D maps that you could perhaps query using very similar like, open vocabulary text queries, or maybe even more? So in this work, we try to augment 3D maps with these variable multimodal features. And the idea here was, can we lift features from 2D to 3D via SLAM? But the challenging aspect was, well, Dino gives you one feature for each pixel in the image, so it was natural to lift to 3D by multiview fusion or averaging. But if you look at multimodal models like Flip, they take a single image, like an image of a dog, and give you a single vector or an embedding for that full image. They don't give you dense information at a pixel level. And how do you extract that information? So one way that a lot of people approached this was, let's fine tune. Like, let's take a data set. Let's take a smaller held out data set where, in this case, models like LSEG and OpenSeg, they take data sets with dense segmentation captions, and then they take a clip backbone and fine tune it for the dense prediction tasks. So for each pixel, you have a class label, and you can use that class label to get a corresponding clip text embedding, and you can then supervise these models. But the thing is, you have far fewer dense pixel level label data, but you have a lot more of web scale image text caption pairs. So, and the other thing is you also need to retrain each time the base model changes, you need to do the expensive retrainings to get like a dense model. But the more important aspect to us was it's very prone to forgetting concepts that Clip knows, but concepts that were absent in a dense fine-tuning data set. So these were objects I could readily find in my living room 2 days before the deadline. So that's what grad students and postdocs survive on. So I was like, let's take these models and let's try to run them through popular approaches like LSEG and OpenSeg. So these were concepts that we verified were known to Clip. Like you can do a reverse image search on Clip and figure out whether these objects are known. But when you fine-tune these models like LSEG and OpenSeg, they just don't get sharp responses for models of interest. Like if you're looking for Lysol, you don't get high enough response on primitive concepts. So the idea we had at the time was we still wanted to be training free because the pace at which this.
I thought that for those tasks, we don't need to fine-tune the data itself. Actually, usually people will kind of employ a frozen clip encoders and extract the features and find those features in a kind of open category.
Yeah, so
and I'm not sure in last as you mentioned that private apps are many kind of fine-tuning the clip encoder so you will lose its generalizability. But I'm not sure if you are considering those work that it's just employing a frozen region clip encoders and that series of works.
So yeah, like our work was sort of first in that line where we use a frozen clip encoder and we get like, zero shot features without any retraining.
Oh, yeah.
So yeah, that's the work I'm going to present right now.
Oh,
But
okay.
at the time when we did this work, there were a couple of works, like LSI and OpenSec, they're not required, it's not like you're fine-tuning the clip encoder, you were distilling clip into an entirely different encoder decoder.
Oh, yeah.
So, yeah, that's, again, I'm talking about work that we published in 2020, so we didn't really do it.
Oh, sounds good.
The field moves really quickly. So yeah, I'm glad we brought it up because I'll also talk about follow-ups. That's
Okay.
done.
Okay.
So yeah, our target was we do not want to do any sort of retraining. We want to preserve all of the concepts that Clip knows about, just like we said. And the reason we wanted to do this was you get new models every other week, and you want something that's general enough and that scales with increasing performance of these newer, more capable models. So we made use of the fact that you can decompose or factorize an image into a bunch of meaningful objects or segments. So we factorize this, and at the time we used a very old model from Transformer, but a month after this project came out, Facebook came out with this, Meta came out with the segment anything model. And that made life a lot easier. In many ways, that was a bet that paid off well. So we decompose this object, this image into a bunch of constituent masks. And then we pass these masks through a frozen clip encoder. So we encode the full image through the clip encoder, and we also encode each of these individual object masks through the clip encoder. And then we try to compute like an all pairs similarity between the global image level features and the local mask level features. And this similarity score intuitively tells us how much of the image identity is determined by just this one single mask. It helps us identify which masks are more dominant in asserting the overall identity of the image and which masks are less so. And you can do these to assign a weight to every single image pixel. And one of the things here is you can now do like a 2D version of this where when you now search for text query teddy bear, you can delineate all of the pixels that correspond with concept, as opposed to just saying this image, yes, it corresponds to a teddy bear. Similarly, you can do this at a pixel level. And you can also extend this to multi-class segmentation. So far, it's all just 2D, and we also then lifted this to 3D segmentation. But before then, just like slide detour, see, like revisit that example we had and see how the strategy performs. So you can see that you have a much sharper transition, and you are able to detect all these concepts that are available in the clip space. And these models lose out due to fine tuning and these concepts not being present in the fine tuning data set. Yeah, so just to recap, we used the strategy I outlined above to compute like 2D features, per pixel 2D features, and you look them the 3D SLAM, and you get better representations because you fuse information across multiple views. So even if you have segmentation or clip extraction noise for some views, other views tend to upgrade, and you don't need any training or fine tuning, and you can apply this to any clip backbone and not just the one backbone I presented earlier. Something very interesting happens when we start inspecting these features over 3D space. So what you see here is like a k-means cluster with increasing values of k over these clip-fused 3D maps. And you see that regardless of whether you use clip or dino, just doing a k-means clustering seems to factorize the scene into very meaningful sets of objects or semantic concepts. You have like walls, floors, ceilings, and maybe furniture that starts to emerge. So we then extended this to do 3D text queries. So the idea here is you would present a text query in 3D. So you would have a query that says it likes to say watch TV. You import it, you get the text imported to get an embedding. And you compute a dot product between that embedding and every single point in the scene. Because again, it's a constant time operation, even for a large scene, if you assume like large GPU memory, more about having it done more efficient data. But you can also do more. Like there's clip models that are also aligned to audio representations. So you can play a ceramic blinking audio and then ask which objects in the scene might produce this sound, and you can determine it was. You can also, like, this was a random cabinet image that you typically find on the first page of Google search for some cabinet, and then you can locate the cabinets in this loop. And another thing, so one of the queries, like, maybe you just click on one point and then get all the points in the scene that correspond to that segment. So if I click on one point in Islam, I get every single point that corresponds to the same concept. And this was indeed what I wanted to do this project for. Like this concept fusion was an annotation project gone wrong. So I was collecting lots of data and I wanted quick ways to annotate this data. And I was like, maybe clip features make sense or dino features make sense. And that drove me to this rabbit. So if you look at performance, and we can skip some of these time, but these two models were LSEG and OpenSEG, which were pre-trained, which assumed fine-tuning. And this was the previous best non-fine-tuning baseline, which was actually concurrent to us. So we do a lot better. And these are on classes that have been vetted to be absent in a fine-tuning data set. So these methods are English. We're talking about concepts that are not present in a fine-tuning data set, but along the clip. And image query trends, we do better. And even on concepts that the fine-tuning models have seen, we don't lose out too much in terms of performance. So the rightmost is ours. And these models have actually seen per pixel dense data from all of these models. We don't lose fully. And we then used apply these models to navigation. So a text query roundabout, and we have like a laser scan map of a block campus, and you use the text query to identify goals and autonomously navigate these goals. And you use the roundabout. I'll skip the next query, but you can also do manipulation. So you can give queries like move Baymax to the right, and you're able to identify pixels corresponding to Baymax and move it to the right. There's more, but we can talk about it after. And we can also do any clip backbone. So I showed audio clip as an example. We can also do multilingual clip, where we now show the same query for 6 different languages. But then there's lots of, so that was the first attempt. Well, there we assumed you can construct like a large 3D map, like a map of this room would have 8 or 9 million points if you're thinking about very dense high resolution representations. And then each of those points having a clip embedding just takes you out of GPU memory very, very quick. So can you do better, especially if you want to deploy it on a robot? So we came up with an approach that would use open vocabulary detections or segmentations. So you can flexibly use either detections or segmentations or both, and extract objects, associate them across time, again using Clip and Dino similarity scores. So you have a 3D object-centric mapping approach. And in addition to building a 3D map, we also detect relationships, support relationships, spatial relationships between these objects, and organize them in a 3D scene graph. And you can also extract visual information like captions to describe each of these objects, which gives you a 3D scene graph that can also be aligned to some sort of language model to do more abstract queries. So in this example, we do a parent query, which is like, so we say, get me something that goes well with an Ronald McDonald outfit. And the language model reasons that a Ronald McDonald outfit is typically red and yellow, so there's red and white sneakers in the scene that might go well. There's also queries that have both visual context and text, where we have like an image of Michael Jordan and then say, get me something this person will play with, and model associates this with a basketball that's lying around the scene and navigates the basketball. There's more examples of what happens when objects are missing. You use scene graph to search for other analog locations where these objects could go, and you also update the scene graph. But I'm skipping all of that in interest of time. But in the few months that this has been out, we've seen lots of interest. We followed up on it for sure, but there's also a lot of other groups that started following up on it, like trying to do exploration, try to do 3D or multimodal language modeling and also apply this to other domains. I will also skip through some of these. There's one more work that I can talk about in some of 1 month, but just summarize, the idea here is building open vocabulary structures and representations just unlocks new capabilities, particularly in the context of robots, but retaining algorithmic structures like SLAM or symbolic structures like scene graphs is very important. And being model agnostics helps as newer models are released and performed in improves. So far I just talked about the work I've done. I'd also like to take some time to talk about what I see as like research frontiers here, where are lots of application areas or avenues for further work. And one of the areas is physical understanding, which I did not talk about in the earlier parts of this talk. But in terms of physical understanding, we've had a lot of work. So back in my PhD, I did a lot of work thinking about what kind of computational models that can be developed for physical understanding. And or here, the goal was, given a video sequence, can you infer the physical properties of objects and infer maybe controls from just the one video sequence, or in some cases, just an image. And the way we did this was design a generative model, or when I say generative model, it's a computational model that specifies how the observations arise from inputs. And in this case, we take the object descriptions, run them through a differentiable physics engine, and get states which are passed to a differentiable renderer, which synthesizes a video. And you compare these videos with predicted, like you compare a predicted video with a ground truth video, which defines a loss. And since this entire system is differentiable, you can backprop and figure out object physical properties and also controls. And the first version of this work was somewhat restricted. It could do things in simulation where the exact model was known. But over a series of works over the last 2 or 3 years, we extended this to not knowing the geometry and not knowing the rendering configuration and working in the real world on robotics tasks involving deformable objects like plot here. It's also a couple of fluid examples. And we also did work on assessing the loss landscape through these simulators and how we can explore more basics of convergence. And how do we even characterize uncertainty by bringing in aspects of probabilistic programming in addition to differentiable programming. And there's also been adopted by a lot of others, and people scale it to other kinds of physical systems, develop learning algorithms. And in future, one might want to look at how we could move away from having to know these accurate models to models that are more intuitive. So imagine this kind of contraption, even though you've never seen something like this before, maybe some of you have, but you can conceive how you might drive one of these fancy bikes. Or if this is your first time playing Jenga, by looking at other people playing Jenga, even if you're not simulating the accurate Newtonian mechanics of the Jenga blocks, you can get some sense of what are good and bad actions in this context. So can we move away from requiring detailed models towards more intuitive models, like models that are perhaps false, but you compensate for this by baking in uncertainty about your predictions and uncertainty in your model. So you have something that's wrong, but as long as you know that that model might be wrong, you're good. Or you can use that in many interesting ways. And that's what robotics do. Like they rely on models that are faulty, but build in guarantees around it based on uncertainty estimates. So again, the motto here is, can we scale, like instead of scaling the number of parameters in the transformer, like instead of strapping 1 million more parameters, can we increase simulation capacity instead? Like, can you think about alternate paradigms where we have massive amounts of compute going into simulations? So in terms of spatial understanding, how are we on time? I have 2 more
I haven't
slides.
been paying attention. Carry on, it's very interesting.
Okay, so yeah, I just have like 2 more slides and I will end there. And when you think about spatial perception, like there's all of these interesting models, like the Sora model here being released, and they all work on, they're not trained natively on 3D. They're trained only on videos, 2D videos. And the reason is that there's just a lot of them on the internet, and that's perhaps the only scalable data source we can find. But you can imagine a future where these are trained natively in 3D. But the hurdle to getting there is that you don't have any structural motion or SLAM techniques that can work on scenes like these, because these are all moving objects and these are discarded as outliers in any SLAM or structural motion context. So we've had some initial steps where with a very skilled master student that we've been advising at MIT, we started to design pipelines where you can go more intuitively to interact with objects, and motion, which is actually the single biggest cue to detect object rest, is being leveraged as a first-class citizen as opposed to just being discarded in one player. And this becomes all the more exciting with all the work we're seeing on like dense correspondence tracking. So this opens up new opportunities to rethink SLAM or structural motion with these new toolkits we have. And that might enable learning from these scalable data sources. And the last idea I'd like to touch upon is this notion of multisensory reality capture, so this is a result from a SLAM system we released earlier this January, and you can very faithfully reconstruct and render these, and this seems very realistic in synthesizing novel views of the scene, but imagine going beyond vision. Like imagine being able to drop a ball and hear what it might sound like, or being able to like scrape the surface of the wall or the table and feel like what it is to touch. So the next generation of learning algorithms could tap into these sort of multisensory replicas that go beyond vision and incorporate tactile sensing, auditory perception, and these can be like rich test beds or like simulators that are more close to the real world. You can deploy robots in that's the crib where they learn how to interact out in the real world. And again, like taking all of these and like projecting it so much forward, like say 20 or 30 years forward, there's new patterns you can think about for robot learning. Like the key idea is to not build like robots that are capable of doing everything, but rather build learning machines that are capable of learning or being taught new pieces of knowledge as opposed to knowing everything on the first floor. So then you can have robots, deploy them out in the world, they gather data, and to become more capable, you can deploy them across more and more applications to gather even more data, and this virtuous cycle continues. But then again, to establish this sort of cycle in the first phase, you need some structure. So what's built in versus what's learned, that's where the trade-off comes in. Like structured world models are kind of what can kickstart this virtuous cycle. And this is not saying that this is just the one research agenda, which is about everything. We need lots of help from a lot of other advances. And also I just list 3 bits here. There's lots of bits that are all existent, like social interactions, for example, planning, learning new skills, executing them more reliably, safety, robustness, and maybe deploying all of these capable systems in real time. So there's lots of avenues to collaborate on. With that, I thank collaborators, advisors, and mentees, and yeah, a little over time, but happy to take questions from anyone.
Yeah. Okay, well, thank you very much. Questions?
You mentioned that motivated during the multimodal understanding that when you fine tune the clip models, they lose their generic performance. So I didn't really get how do you counter that?
Yeah, so the question was when you fine tune clip models, they lose their generality. And we studied that not just in our work, there's a couple of other papers that kind of established at the same time that you need to continually keep adapting these models. And the way we do that is by not fine-tuning a clip model. And the idea is when you fine-tune, you start drifting away from what you've been trained on and you start specializing on the concepts you have in the fine-tuning data set. And the fine-tuning task here is a lot more dense than the original task. The original clip model just has to match like a single embedding to a single text vector. So the fine-tuned model has to extract an embedding for every single vector. So we hold the clip model frozen, which means that all of the things the clip model was capable of inherently are still preserved because we're not altering the weights of the fluid model in any way. We're just factoring the image, the different segments, and like figuring out which pixel gets which feature. So that way, if there's something that the fluid model knows, you are still preserving it because it's identical to the model that was before. And unlike in fine-tuning examples where the fluid model weights change, in our case, the fluid model weights stay the same.
Yeah, hi. This is Russ Taylor. I'm out in TV land today. Could you talk a little bit more about how you would deal with uncertainties and errors in your yellow and green circles there? You mentioned dealing with uncertainty in terms of the physics, but if you see something that you've never seen before, are you likely to say, oh, that is most likely a teddy bear with some confidence, or what are you going to do? How do you deal with that?
Yeah, so that's a good question. So as long as we're talking about semantics, I think dealing with uncertainty is a very open problem. I don't think all of these models like Click or even like language models have good safeguards for what happens when you're outside of the training distribution. So in this case, if you were dealing with a new object that you hadn't seen before, you would likely map it to the closest concept in the embedded space. So you map it to something very close. But then I think the opportunity here is in terms of like both spatial and semantic. You can capture, so uncertainty can be captured in the spatial sense. There's recent approaches that are trying to capture uncertainty within a trained neural representation of the scene. So that there's progress in that. In terms of semantics, one example we did was quantifying the uncertainty inside an object detector. And this was like a closed set object detector, which is trained to detect just 20 classes. We did work on quantifying that uncertainty by analyzing just label distributions of the training set and label distributions of the actual like data itself and trying to align them. So, but then that's all work. So that does work on this on this portion of the slide, like bounding boxes we see here on the cars. You see ellipses around the bounding boxes, which indicates how uncertain those are. And one other example I showed you is like per point confidences, like where you could basically assert that the shadows and the moving objects are a lot less confident. So those are some approaches I've tackled in my own work, but there's a lot of literature on uncertainty quantification and pretty much open problems for the next many years for the community to solve it. I don't know if that answers your question.
Okay, well, thanks. It's a longer discussion than we have time in a question period. So,
For sure.
but these systems generally lack humility.
Sorry, I missed that last word. You said these systems generally lack. What?
Well, so I think you can have a chance to talk later. I guess we're still not here today, but maybe you can arrange a Zoom call with Krishna later on to have a more detailed discussion.
Might have question to be curious more about this physical understanding part, like what kind of differentiable it does in this
Yeah, so we built a variety of differentiable simulation engines over the years. When we started out, it was all force-based simulation, but now we also moved to where it's like FBM style methods, more particle-based methods. And more recently, we're also trying to use like black box as opposed to having it fully differentiable. Can we use black box simulators and scale them up, like scale probabilistic instance using black box simulators up? Well, that direction is pretty much experimental right now. But yeah, it's all across the board. And there's a lot of other groups which adopted the same paradigm, but everyone built their own simulation engine. Like there's groups that want to deploy this paradigm for clock, and they would build like specialized simulation for clock. And there's groups that are trying to specialize this in molecular dynamics. They will build their own engine. I don't think we can have like just the one simulator simulate every single, like even if you think about simulator in your head, you're probably not simulating how every single like leaf out of the window moves. You have like an attention span of the task you're focusing on. And it's very contextualized just to the level of performance you need on that task, where it's like a surgeon trying to perform precision surgery versus like a kid that's just trying to understand how it's working.
Okay. More questions? Okay, if not, I've got many questions, and many attempting to ask you them now. Otherwise, well, thanks, Krishna, for a really interesting.
Thanks.
Please do.